Okay, this is the second lesson of lesson number 7. This is the second part of lesson number 7. We're going to be covering sections 17.7, 17.8, and 17.9 in chapter 17 about combining normal and shear stresses. Okay, this kind of builds upon what we talked about on stresses on the inclined plane, but from our study of beams, we learned that two kinds of stresses can exist at the same time at a given point in a loaded structural member that's in equilibrium. There can be normal stresses due to bending, and there can be also shear stresses due to the general shear formula. So, for us to further understand what's going on here, we're going to consider an infinitesimal stressed element where both shear and normal stresses exist. Okay, so here we have a beam. Okay, we take an element out of it that is not on the neutral axis because the bending stresses are 0 at neutral axis, and it's not at the outer fibers since the shear stresses are 0 out at the outer fibers. So what we have going on here is we have a horizontal shear stress, we have bending stresses, and that's what we got going on. We got horizontal shear stresses and then bending stresses. Now we know that shear stresses cannot exist on a plane by themselves. There has to be an induced response on an opposite plane. That's why we have these arrows here, and we talked about that in chapter 11. So now, here's our stressed element. We have our shear forces, we have our shear stresses here, shear stresses, and then we have our forces. This is just a generic one. So we have shear stresses, that's our FV, and we also have normal stresses in the y direction and the x direction. Okay, so from our study of beams, we know that the location, orientation, and magnitude of both the bending and shear stresses at a point in a loaded member. So we know what's going on at a point, we know what the shear stresses are, we know what the tensile stresses are due to, and compressive stresses due to bending. Okay, so by studying the stress at different plane angles, theta, we can derive a better understanding of the state of stress at that point. So this is not unusual for a loaded member to have stresses in two directions and two different kinds of stresses. So if you were a structural analysis, you would have to take a look at what was going on at a certain point in your part. You would know that there's tensile stresses there, bending stresses, there could be compressive stresses, and then what we need to know is find out what are the maximum stresses due to this combination of stresses. And that's really what combining normal and shear stresses is about, what we're trying to do. So what can we do in section 17.7? Okay, section 17.7 allows us to derive a bunch of equations based on a free body diagram of the stressed element. These equations are, what is the magnitude of the normal stress at any angle? Okay, this is kind of like what we did in chapter 11. What is the magnitude of the shear stress at an angle theta relative to primary axes? Another equation we have is what is the orientation angle theta of the principal planes where the normal stresses are at its maximum. Okay, when I say principal planes and principal stresses, that's kind of meaning something very similar. What we look at when we look at the stress element, if we can look at this at different angles like we're trying to do, we can find the point or the angle or the orientation of that element where the principal stresses, when I say principal stresses, I'm talking about normal stresses, are their maximum and their minimum. Okay, so if I was a structural analysis, I would be looking for what these principal stresses are. Okay, and typically what we do is we rotate that element to the point where there are no shear stresses, and then the normal stresses that are left over are going to be at their maximum. So those are principal stresses. Also, we can determine what the orientation angle theta is for the planes of the maximum shear stress. In Chapter 11, we looked at this. We found out the maximum shear stress is typically 45 degrees to the maximum normal stress. The magnitude of the maximum shear stress, we can find that there, and we can find the magnitude of the normal stress at the orientation plane of the maximum shear stress. Okay, so we find the maximum shear stress, we find its orientation, and then we'll find the magnitude of the normal stresses at the orientation where the shear stress is the maximum. So how do we do this? We're going to do this in section 17.7 using a bunch of equations that we derive from this free body diagram. Equation 7.6 through 17.12 are derived using this element, cut at the inclined plane, orientated theta from the normal axis. Okay, essentially all we're doing here is we're taking our infinitesimal element, we're cutting it at a plane theta, and then we're summing these forces together and solving for what is the normal force at this plane theta and what is the shear at this plane theta. We're looking at this in terms of stresses right here. This F sub n, that's your normal stress, and then F sub v, that's your normal shear. But to do this properly, we have to look at things in terms of forces to get the balances right. I'll let you look at that, but let me summarize these equations now. You can use this as a reference. Okay, here's equation 17.6. That's the normal stress at an inclined plane. Again, derived from those free body diagrams. And then equation 17.7, here is the stress, shear stress at the inclined plane. 17.8, what is the orientation of the principal planes? We're going to talk about this in detail here. And then what is the magnitude of the principal stresses? Okay, there's always a min and the max principal stresses. Okay, so that is the thing that's probably the most important to us right now, is what are the magnitudes of those principal stresses. 17.10, planes of maximum shear stress. So you're solving for this theta s here, which is the plane of this maximum shear stress. Here is the maximum shear stress formula. And then 17.12 is the normal stress at a plane of the maximum shear stress. Okay, so these are our formulas for determining the things we need to determine. And then in 17.8, okay, I'm going to go through an example with you. It's in the examples in the problem section, and it's going to be this example 17.7, where we're going to use this stress element to find some of these parameters that we just talked about using the equations. Plane. Okay, I think I'm going to end this one right here. Go view the example problems for the second set of example problems, because we're going to talk about how to use these equations in section 17.7.